Okay, thank you for the introduction. And what I will talk about is how we can look at polymeric structures, and then both at really short length scales, but also at larger length scales, approaching device scale, which would correspond, of course, to typically the millimeter range, microns to millimeters. First, a few words about my research group. We are working on soft functional materials, polymers, organic electronics, MEMS and microsystems, and we also have national infrastructure for X-ray scattering and imaging. And the, let me see if I can find this. And that it actually works. Nope. Well, I have another pager here, so let me try to use this one instead.
Okay. Okay, så du har en selv?
Yep. Okay, here we go again. Maybe? Yes, so we are working on polymer physics. We are working with thin films and grazing incidence. We also work with X-ray imaging, and we also do a bit of X-ray physics. And what I will be talking about here is in this category up here, grazing incidence and also tachography. Organic electronics deals with, well, here are various ideas for what it can be used for. And one of the central pieces here is field effect transistors. And based on these transistors, one is thinking to make electronic papers, wearable electronics, cheap dynamic signs, sensors, etc. And this is to some extent already commercialized or close to commercialization, like for example in the form of OLED screens and electronic paper. So what I will discuss here is that I will in the first part talk about the small scale structures, molecules, and a bit longer stuff like mesoporous thin films. And then in the final part, I will be talking about coherent imaging and so-called tachography. So why would you like to use grazing incidence? Well, that is because it is a non-destructive and quantitative technique that allows you to study thin films. And the sample preparation is easy. You don't need a ultra-high vacuum, and the interpretation is also relatively simple. And this has become a very powerful tool in organic electronics. I mean, 25 years ago, roughly, people started to use this technique. There were not so many people doing that at the time. I think it was considered some kind of exotic. But these days, it is, I would say, getting close to rare that you see an article on the new polymers for field effect transistors or solar cells where people have not been using this technique. So it's really becoming very widespread, and yeah, so of course we appreciate that. A modern X-ray source looks like this. This is the synchrotron in Grenoble. You have electrons flying around here at roughly the speed of light. And then in magnetic structures like here, the electron is forced to wiggle back and forth, and because this is then an accelerated electronic charge, it will emit X-rays, and these X-rays can be used to study a sample by looking at the details of how these X-ray photons are scattered. So in the particular technique of grazing incidence, one has a thin film on the substrate, one has some kind of molecular or otherwise structure here in the sample, and one is looking at what kind of scattering pattern that one gets on the detector, which can be either rather close to the sample to catch wide-angle scattering, or one can move the detector further away if one is more interested in scattering to small angles, which would then correspond to larger scattering structures. Yeah, we have published quite a lot of, here are some selected examples of works that we have been doing with this technique. So how does it work? Well, I suppose that you all know Snell's law about how light is refracted when it goes into a material like glass. And then, as you know, the index of refraction is typically close to 1.5 for glass, roughly. Whereas for X-rays, I think the first thing that you learn about X-rays, maybe already in primary school, is that X-rays, they go straight through, right? They go through your body, for example. So then you can maybe also guess that this implies that the index of refraction for X-rays, because you know X-rays are electromagnetic radiation, just like light, it just has a higher frequency, but the index of refraction is close to 1, right? It is almost exactly 1, it is just a millionth of a, so 1 times 10 to minus 6, below 1. So the refracted beam is almost parallel to the incoming beam. But what is more interesting is that because the index of refraction is a little bit less than 1, this means that the refracted angle is opposite to what you are used to with normal light. So in other words, if you make the incidence angle, if this is your substrate, and you are sending an X-ray beam in here with a sufficiently small angle of the order of 0.2 degrees, the beam will be refracted upwards and be reflected off the substrate. Right? So this means that even though we are working with hard X-rays that are famous for being extremely penetrating, the X-ray in this case will not go into the substrate, it will be reflected off. And because of this, it will be extremely sensitive to whatever material you have on the substrate, right? So in this case, it is a thin film, and you can see we get essentially no background scattering from the substrate, but we get scattering from inhomogeneities in this thin film, which happens to be deposited on the substrate. Was that clear? Yeah? And there's one more concept that I would like to just briefly mention for you, which is that these thin films that we are looking at, they are often spin cast, and they also tend to be semi-crystalline, these materials, meaning that in between amorphous regions, they also have some more crystalline regions where the polymer strands are rather well ordered. Right, but because the material is spin cast, this implies that typically you will have one unique axis which is parallel to the substrate normal. So the polymers will either tend to be upright or perpendicular to the substrate, if you like, typically, or having some other kind of fancy organization. But in plane, the orientation will be random, right? So you will have some crystallites in this direction, same probability of finding them in other directions, right? So for those of you who are familiar with reciprocal space, this means that if you think of the Ewald sphere and the incoming X-ray beam like this, any reflection HKL will be, instead of just being a point in reciprocal spaces, as you are used to when you think about a single crystal, it will be smeared into a ring here. I will come back to why that is significant, but first I would like to mention that we have developed software for modeling exactly this kind of problem, and it has gained popularity which significantly supersedes what I was imagining when we published this. So people are requesting this software quite frequently, and I think the reason for that is just the intuitive use that you can think of. In this case, for example, it is some small organic molecule which has some reported unit cell. You can download it into the structure and you can simulate what you expect the diffraction pattern to look like for different orientations of the unit cell with respect to the substrate, which you can see is illustrated in gray here. So as an example, this is the small organic molecule perylene, which we can also deposit on friction deposited PTFE, which is famous for being an alignment substrate for a lot of organic molecules. And the scattering patterns can typically look like this. So you can see that this is a very crystalline material, judged by the fact that there are all these strong Bragg peaks, and you can also notice how symmetric the pattern is, meaning that we have this fully randomized in-plane orientation that I mentioned for you. But you can also notice that there is no smearing of the diffraction peaks radially here, which implies that these molecules or crystallites really have a very well-defined orientation with respect to the substrate, right? And if we put this on Teflon, as I said, we can also measure various rocking scans, and we can figure out how these molecules, how the crystallites, to be more precise, are oriented with the alignment substrate. Yeah, so here is one example where you can see that the PTFE polymer strands are indicated by these gray lines here, and we found that the perylene unit cell always took this orientation, which also implies that these organic flat molecules are standing edge on onto the edge on with respect to the substrate, which we can also then simulate in the off symmetric case. You can see again that there is a very good correspondence between the experimental and the simulated scattering pattern. Here's another example where we were looking at polymer blends, some roughly 10 years ago, which was polyethylene, which has a unit cell which looks like this, where the chain now is coming out of the plane, out of the screen. Whereas here you see a polyhexyl thiophene, and here the main polymer chain is clearly running in this direction. Right, so in both cases, with the orientations I have shown here, the polymer backbone is parallel to the substrate. And then when you look at the scattering pattern from this, these turns out to be, these reflections you see here turn out to be from polyethylene, and these structures are from polyhexyl thiophene. And then the interesting part was that when this is correlated with the field effect transistor measurements and with the use of both isotactic and atactic in different experiments, and clearly materials, so either highly ordered, so to speak, polyethylene or more amorphous material. The source drain current is 3-4 orders of magnitude different, right? And also when we correlate this to the scattering patterns, one can see that clearly in the atactic polystyrene there are no sharp diffraction patterns consistent with this material being roughly amorphous. But what is more interesting is that the electronically active material, the polyaxial thiophene, the crystallization of the polystyrene promotes the crystallization of the polyaxial thiophene. So if you want to read more about this, you should look into Nature Materials from 2006. Another story which also goes on materials of interest to organic electronics, cadmium selenide, which is famous for this series of solutions, right, where you can see that their colors is size dependent. As I suppose you all know, this is a quantum confinement effect. If you look at these rods with an electron microscope, you will typically see something like this, where this is it has been deposited onto a substrate, gently rubbed like this. The rubbing direction is like this, and you can see that there is indeed some alignment of this cadmium selenide with the rubbing direction. You can also notice that some of these particles appear to be darker, and the reason for this is that this is TEM, and in TEM you have diffraction contrast, right? So those of these particles that happen to be oriented such that the diffraction condition is fulfilled will in this pattern appear to be darker, right? Because intensity will be diffracted out from the main beam. Yeah, so we developed this model, parameterized structural model, to deal with these different aspects in terms of orientations and shape of these particles, and we're indeed able to model this quite closely. So, yeah, the crystal structure turned out to be Wurtzite, and as one could guess already from the TEM images, the long axis tended to be parallel to the rubbing direction, and the AB plane of the crystal structure was parallel to the substrate. So they were biaxially oriented, these particles. In the next part of my talk, I will briefly go through a little bit of GSACs and mesoporous thin films. So the technique is roughly similar to the one that I already described to you, at least conceptually it's similar. The difference is that we will now be looking at somewhat larger structures, right? So instead of looking at Bragg peaks that are originating from molecular or atomic planes, we will now be looking at pores or micelles, right? So they are typically an order of magnitude bigger. And this means that we need to put the detector farther away to be able to catch smaller scattering angles with some resolution. So as you probably know better than I do, the way to do this kind of stuff is that one puts surfactant micelles in, for example, alumina or silica precursor solutions. This is the sort of Sol-Gel technique. One can have micelles forming, and when this solution dries up, one can make them spontaneously self-organize into various crystal structures, and then in subsequent calcination steps, one can make the precursor solidify, if you like, and at the same time burn away the organic materials. So here is what that typically looks like if you look at the thin film using a scanning electron microscope. You can see that there are these extremely regular long-range ordered structures that can, for example, be hexagonally packed or also assume other structures like FCC packing, for example. Yeah, so all these packing patterns have their kind of reciprocal space or scattering pattern fingerprints, so that one can easily, or with some modeling efforts, be able to distinguish between them. And as I said, these pores or micelles that are self-organizing here, they are doing this in a very regular manner. They are forming long-range ordered crystals. And because of this, we can take the formalism that is well known from crystallography, where we just replace the form factors that are usually just describing the form of an atom. So it's typically just some isotropic scattering function, right? With a function which actually describes the shape of the pores that we are looking at. So rather than going into the details about that, I will just mention briefly an example with silica that was templated using the organic molecule CTAB. And this forms a 3D, so-called 3D hex structure, which looks, the scattering pattern looks like this. And I'm not expecting you to see anything suspicious here, but there is in fact one thing which is a bit surprising, and that is that if you bother to calculate the structure factors, you will see that there should have been some diffraction peaks here, right? You can see that there is some remnant intensity here, but it's almost gone. Whereas from naive calculations, you would have expected this to be a significant diffraction peak here. So what can the reason be for this? It is allowed by the structure factor I mentioned for you. The other factor that comes into play is the form factor. So what if we can just play a bit with the form of the micelles to see if we can model this? So instead of taking the micelles in this case to be spherical, we can assume that they are slightly compressed. And if one does that, one will see that the minimum of the scattering function actually coincides with exactly these positions here. So what that implies is that we can probe the shape of these pores with a few angstrom resolution in this case, which I think is a very cute result in this respect. Right? So we can really prove from the scattering pattern, which and this has been observed previously in calcined films that you look at with electron diffraction. You can, or directly with electron microscopy, you can see that the pores are indeed a bit collapsed in the vertical direction, right? But it's really cute that we can do the same non-destructively in the non-calcined state, right? So one can really see that these micelle structures are already in the thin film phase, non-calcined, a bit deformed in the vertical direction. Yeah. So that was this stuff. Let's jump across this. We have also done similar stuff on mesoporous alumina, where you can see that there are lots of rather similar, closely related structures that can be modeled along these lines. Yeah, I think I will go to the next part of my talk, which is now I was talking about diffraction. I started at the molecular level, then I was talking about the mesoscale structures of these mesoporous systems, and now I will be talking about X-ray imaging, starting with the traditional stuff, the hand of Professor Röntgen. And curiously enough, people are still analyzing this image to check whether she had arthritis and so on, right? And then I would like to show you, just to emphasize a bit on the power of working in 3 dimensions. Just look at this. This is so far just some flower that you see in late summer, right? And it is with an ordinary video camera. And I think it is beautiful to notice how you can really see the 3-dimensional structure of these beautiful. Just pick one up in summer. I really recommend it to take a close look. They are really beautiful. Look at these structures that you are able to observe here, just because this thing is rotating, right? And then by using X-rays, we can then study the very same old flower, but now, because of the penetrating power of X-rays, we can also scan through it. And if you are confused by what these things are, these are the seeds that are still hanging here, and they are the only ones that actually absorbs the X-rays, right? And clearly here you can see the interior by standard tomographic methods of what this flower look like. Quite nice, right? And this is of course an easy thing to do, and it is macroscopic, but it illustrates for you what you can do with X-rays and what you can do in 3 dimensions, right? So yeah, here you really see clearly the interior of this flower now. Yeah. So then the question arises, can we extend these ideas to be working so that we can work at the length scales that we need, which would be 10 nanometers typically for organic solar cells. Existing technologies that come to mind include focused ion beam, SEM, TEM tomography, but these are all invasive and they are destructive. There is difficulties with sample preparation. This TEM requires ultra-high vacuum, and how can you possibly do anything in situ in this way, right? It's not possible. So one possibility is to use coherent X-ray imaging, and the way that this works is that one is exploiting the coherence of the beam. The coherence of X-rays is something that you can find at the few selected X-ray beamlines at synchrotrons. It's not what you find in a normal laboratory source, for example, but coherence means that the light has the kind of properties that you find in a laser, right? And one of the key consequences of coherence is that you have stationary interference patterns. And because you can have these stationary interference patterns, which is basically because all the phases are sort of fixed with fixed phase relations, right? And the color is rather monochromatic. You don't have this polychromatic mess that you see in the other cases here. This is clearly the coherent case, right? Another consequence is that when you have these stationary interference patterns, you will also observe speckles. So if you have a laser pointer and you don't know what speckles are, just try to shine it onto a surface and look at it closely, and you will see all these fine-grained structures that are due to the fixed phase relations in the laser beam, right? So what we are doing is that we are sending the coherent X-ray beam through the sample and looking at the speckle patterns on the detector, and numerically one can, under certain circumstances, numerically reconstruct the object based on the speckle pattern, right? So one can really calculate from here the way back to find what the object looks like. That's turning out to be a very popular or upcoming technique. It turns out to be very powerful, and it's a very hot topic, I must say, in X-ray science, but also increasingly in material science for obvious reasons. And one example is here, where you can see a calcium carbonate, small kind of agglomerated structure, where you can see a calcite, small crystallite here. And this indicates the scale bar here, so we are down at 5 micron, right? And being X-rays, we can clearly also resolve what the particles look like inside. And if you look here, you see that that whereas the calcite crystallite here, this polymorph is dense all the way through, these other agglomerates are in fact porous inside. And again, it's nice to be able to see this non-destructively. Here's another example with a related technique, which is, should be of relevance to this audience, where we are looking at a stack of organic materials, PDOT, PSS, zinc oxide, etc. It's a tandem cell, meaning that there are two photoactive layers here to increase the performance. But our motivation for looking at this is to see whether we are able to dissolve the various layers. And indeed we are, and this study could also be correlated with the performance of these cells to point out like that short circuits like the one that we have resolved here is reducing, of course, the performance of the solar cell. So to the best of my knowledge, I don't know of any other technique that is able to really distinguish between these organic layers, to look at the thicknesses and roughnesses and so on, and to do this non-destructively. That's quite nice. I think I will skip these examples and rather just focus briefly on the study we have done on Ugelstad spheres, where you have a polymer core, and outside, in this case, these are particles from Conpart that maybe some of you know. It's a Norwegian company, where there is a nickel coating, there's a gold layer coating, and there is also an insulation layer. So this is resolved in 3 dimensions to high resolution. As you can see, when we can clearly segment this stuff to look at what is going on inside. And we can also just look at the scattering patterns and describe this analytically, because they are such perfect spheres, these Ugelstad spheres. Then we have also been looking at the destruction of these spheres. So meaning that they are between two punches like this. And people have been doing that here in the nanomechanical lab at NTNU. You can look at the force as a function of the deformation, and you will see that there are some displacement bursts when there are fractures forming either in the metallic coating or in the polymer itself. Right? So we set out to measure this in an experiment. And here is the result. So this is a visualization of the data that we acquired. You can see the polymer coating. This is before we started deforming it, so there were already some defects in the metallic coating. And at like 8% deformation, you can see that there is beginning delamination, which is a key property for understanding, of course, the mechanical properties of these small composites. And then at 14%, you can see that there is now significant damage also to the polymer bead itself. Yeah. For this, we were awarded the front page of Advanced Engineering Materials a couple of years ago. The last experiment that I would like to tell you about today is something that we have been working on rather recently, which is, again, an organic solar cell, again using the benchmark material of P3HT with PCBM. And the setup looks like this. So we have an incoming X-ray beam, coherent, as I discussed to you already. And then we have, instead of just putting the thin film here in the sample position, well, this is the detector, of course, where the diffraction pattern that we are recording. So we have this special chip here, which is a chip which has been designed for fast scanning calorimetry. And this is, I didn't believe it when I first heard about it, because I think it is quite mind-blowing that with this kind of device, one can change the temperature at a range of an estimated 30,000 Kelvin per second, which is just like this, right? It sounds like a joke. That's what you would first think. But then when you consider it a bit more carefully, you can think that in this case, of course, the thermal mass is very small, right? That's the key to this. There's a really, really, really small thermal mass, and there are, I don't think I had more details about actually how this is done, but in the active area here, which is like 60 by 60 micron, there are some interdigitated electrodes providing power to this very thin silicon nitride membrane, and onto this membrane, of the order of 1 micron thick film has been deposited, right? So you have a 60 by 60 by 1 micrometer cube samples sitting here, right? And the diameter of the incoming X-ray beam is a few micron, so that we are able to scan across this sample. And as I said, there are interdigitated sensors, the thermocouples, to keep control of the temperature. And because of all this, we could do experiments, right? So the idea is that the first thing that you see here is the as-cast structure, meaning that the polymer blend had been dissolved in a solvent and deposited onto the silicon nitride membrane, and then the solvent evaporates, of course, and you are left with a thin film. And during this evaporation, solidification, etc. process, some structures are formed in the film. Some morphology is formed, and that's what you see here. The next thing we did was, so this was at room temperature, right? Measured at room temperature, image number 1. Then with this remarkable heating device, we could go up to 550 Kelvin. You can take the temperature difference here and estimate how long time we used to go there. It's instantaneous, right? Straight up into the melt. We stayed in the melt for 5 seconds, and then cool down at the same rate back to room temperature. And then we could measure the structure again, and you can see that the structures have been erased, right? So this is now the polymer structure, which has been up in the melt. Of course, in the melt, all the morphology is sort of blurred out, messed out, disappearing, right? And then by going snap back to room temperature, it's quenched. So it's kind of it's a quenched state, basically. And then we can, for example, go up to this annealing temperature, just below, short of 400 Kelvin here, for say 60 seconds. And you can see that structures are coming back gradually as we increase the annealing time. And the really fascinating thing about this is that you can really separate out the effects of the annealing time from the temperature ramping, right? Because, I mean, in a traditional annealing experiment, you know you would have had, instead of this line here, for example, just going straight down, you would have had something decaying slowly over time like this back to room temperature. Right, so, but with this technique, one can really quench the system back to, and use this systematically to look at the formation of polymer structures. Okay, so with that, I have come to the conclusions that X-ray scattering and imaging techniques are developing very fast, that grazing incidence is the method of choice for studying morphology in thin organic films. It is also becoming a quantitative tool for looking at structures in the mesophase or mesoscale thin films. And then in the last half of the presentation, I told you about these coherent diffraction imaging techniques that currently gives a resolution down to a few tenths of nanometers. Most of what I showed you here was at roughly a resolution of 120 or so nanometers. It's quantitative. I didn't say much about that, but it is in many cases possible to directly relate the contrast to the electron density. And it is a powerful method to get substantial contrast between phases that are otherwise of very similar density, right? And fascinatingly, these can also be combined with various sample environments like the calorimeter that I showed you, and also, for example, the in situ mechanics that I told you about. And with this, I have come to the acknowledgements, and to save time, I will just thank you for your attention.
Do you have a question?
Do you have to travel to Grenoble for all experiments? Not for all of them, but for quite a few of them, we go either to Grenoble or also to Switzerland. I think 2/3 of this work has been done in Switzerland, because the coherent experiments require a coherent beam. Whereas this flower that I showed as an example of three-dimensional imaging, this is something that we can do with our home laboratory tomography machine. So if you have solar cell devices or something like that, where you would like to look at the various structures, for example, or if you have other kind of structured samples with where a resolution of about 10 micrometers is sufficient, then we also have imaging techniques that are useful here. We are not doing single crystal studies, but also this stuff that I mentioned about grazing incidence studies of thin semi-crystalline films. This is also work that we can either do here or in collaboration typically with Jens Wenzel at DTU in Denmark. No, it's not for fun, right? It is because it's not part of a project either, but it's because it's very, I think, very powerful pedagogically. Yeah.
Well, I was wondering a little bit related to his question. Why don't we have that type of cyclotron in Norway?
I think it's not because we don't have money in Norway.
Yeah, of course.
So, but I think, well, there is a synchrotron being built, being commissioned these days in Max Lab in Lund in Sweden. So that will be the nearest one. But I think a different way of looking at it is probably that it's not enough to put the money into buying this kind of machine, because you also need a large amount of motivated and qualified scientists to work there, right? And I think that in the boom that we have had during the last decades in Norway with the oil industry and so on, I mean, there is simply not a national motivation for this kind of large-scale research, I think. That's
I have another question. It's related to when you're sending in the wavelength, the X-ray wavelengths. Are you able to change the wavelengths, so do almost like a spectroscopy, or is that just a silly question?
No, that's certainly not a silly question. That's something that we cannot do in the home laboratory. But and it's something that we usually don't do at the synchrotron either. But I mean, for this kind of experiments. But sometimes one is interested in doing that kind of stuff, and that is because you have the certain absorption edges, for example, and in that case you will have that a given element typically has a very different absorption depending on whether you are just above or just below this absorption edge, right? So this gives you an additional way of playing with the contrast. If it's difficult to distinguish the materials, for example, you can try to play this kind of tricks to have more data for understanding what is what in your image.
Okay, I think we thank Breiby once more.
Thank you.